Okay, from today onwards, that for 6 days we are doing this session. Then after that, you will have the different lecture. Maybe for this part of this section, we are covering the digital electronics module, and you have the one module. Then there you have two sections. The one is digital electronics module. The other one is analog electronics. I am covering the digital electronics part. Okay, I am Sudanta. My name is B.H. Danta from University of Moratuwa. I'm the Dean of the Faculty of Information Technology. Maybe it's unfortunate uh, because of that I cannot see you all, and we can't do the face-to-face lectures at the moment because of this COVID pandemic situation. But anyhow, that we have to do our work and we have to do our studies, and maybe the some of the consequences may be there, but anyhow we have to manage our things. But otherwise, the time is going. We can't catch those that time again. Because of that, we have to bear those things in our mind. And anyhow, you have to do your studies well. But it doesn't mean that if you have any kind of problem, that it should be continuous like this. Like okay, but anyway, that this is your time. At the very beginning, I have to tell you, this is very important. You can remember it, and you have to understand this one. This is your time. This is not my time or with the ICAM time. This is your time. All of us are here because of you, and we all of us, we want you to learn all these things. You not only learning, you have we want you to understand all these things. Because of that, any problem you are having at any time, you can interrupt me. You can raise your hand, or maybe you can write something on the chat. Because of that, I don't at the moment I don't have two screens. So some other days that I'll try to give another screen also. Then I can put the chat and the indications there. But today I'm sharing this screen and I'm recording this lecture also, and I'll put this lecture the recording material on the web. Then you can refer it again. And some of the maybe the colleagues, some of your friends might not join today because of certain reasons. Some of them might have the different problems because of this pandemic situation, and some of them are not having proper connections, and they are maybe the connection may be not strong, and some kind of the connectivity issues may be there. Because of that, some of your friends and colleagues might not be possible to join this lecture. Then all of them and you also refer it again and again when I put these things to the web. And the recorded lecture will be there before you have the next lecture. I'll put that one on the web, and I'll send you the link. And please share me whatever the that I think you have your batch reps. I don't know that what name you are batch representative or or whatever the person. I think he may be the uh, connection point between ICAM and the students. And you can give me your email address, or maybe if you have an email group, please give it to me. And not only you, that I will give that one to the your level coordinator, maybe the your teaching assistant, and from him or her you can take that link also. Okay, please refer it. And if you have any kind of problem, the next day when we start the lecture, before we do anything, you can ask any questions. Okay, but any question is welcome, and we like to see that you are asking much more questions. Then it shows that you are learning. But unfortunately, that as I told you at the beginning, and we cannot see and we cannot have the face-to-face interactions, then I cannot go through the line of the class to see that what are the things you are writing and how you are solving the problems. That is not possible. But anyway, it doesn't matter. That to minimize this effect, you can write anything on the chat, or maybe if it is possible that a lot of other the online writing and different drawing the software are there. You can use those things also. Then you can share it to me, and I can see. Then we can do the correction also. Okay, then, and this is digital electronics module, and this is a very practical module. I'm not telling about other modules also, but anyhow, that when when we compare those things with the different modules, but this module is a somewhat very easy module. But yes, some of you have mentioned that I can't see the screen, but still I haven't shared anything. But I'll share the screen. But okay, I'll do this lecture like this. Okay, that I am opening a Word document. This one, and I'm writing most of the things important. Most of the things I'm telling here, I'll write it there. Okay. Then while I'm writing all these things, and I'll draw all the things in this Word document, and this will be recorded. And I'll upload this video to the web and also this Word document also. Then you can refer both things together. Then, but this is not a complete note that you have to understand that very well. At the very beginning, I have to tell you that I am not going to give any kind of notes to you. It's your responsibility to have your own notes. I'm telling like this because that if you write anything in your own, that is the number one reference material. Because otherwise, that if you use that a different kind of, we have to use sometimes. That if you take a photocopy of a different person note, or maybe if you are taking different printed materials I am providing you, then those things are okay. But anyhow, when it come when it comes to that your note, comparing with your note and other things, the your note is the first one. Why? You have written all these things in your own, and you know why I have written those things and why I have drawn these diagrams, and you know that. Because of that, I suggest you to have your own notes. But anyhow, I am providing this Word document and also the video. Okay. Then today, 5/12/2020. When I open these things, and sometimes that I can't see the chat also, but time to time I will open the chat and trying to see that what you have written there. Anyway, okay. Now, before we start this one, the digital electronics module, before we talk about the theoretical content, and what do you think about this digital electronics? And what do you know about this word digital? If you like, you can write on something chat, or maybe otherwise that you can talk with me. You are free to say anything. What do you think that? Have you heard about this word digital? Most of the time, these online lectures, the students are not talking because on behalf of you, I'll ask the question and same time I'll answer the question on behalf of you. Okay. Otherwise, that if you are interested, you can write something on the chat or maybe you can talk. Okay then. We have seen that a lot of places the digital word is there. And today, when you compare the today's technology world, this digital word is the most popular word. Why is it? Why this digital word is so popular? You can see that a lot of products are coming with this word. The digital phones, digital computers, and digital devices, and digital washing machine, and digital monitors. Like that, the different things are coming into the market, and somewhere on their maybe the somewhere in there you can see that all the time these people are trying to give this digital word there. Then all the people are like to buy those things. Why? Then that name is there. Hello, hello. Oh, maybe you're the one. Okay, why is that? What it means field of electrons with digital signals. Okay, that's I have received one answer from you, and but when you go to the market and when you go to the outside of any place that you can see that most of the products are coming with this one. Then because of so many reasons, maybe I don't know that whatever the reason that you have thinking about, but because of certain reasons, most of the people like this. Okay, do you like digital products? Yes, Anupa. Why? Can you give me one reason that Anupa has mentioned that he likes this one? Yeah, it's easy to handle. It makes everyday task easier. Okay, then you can see that. I think all of you can see this chat. That what are those answers? Those answers are negative answers or positive answers. You can see that some kind of positive flavor is there. Okay, it is easy to handle. It makes everyday task easier. Like that, that you can see some of the responses are coming. All these things are coming, going to the positive side, not to the sometimes the negative feedbacks may be there, but most of the feedbacks are positive. Why? We like it. Why do we like it? Because of these reasons. Okay, but if you come to that then as you mentioned that may be easy to handle and still more features. And what else? What about the size of those products? But when you compare that the maybe the couple of years back uh, in your dining in your living room that you had a big TVs, the CRT tube TVs. Now you have LCDs or LED TVs there. I think you might not have any experience that maybe the couple of decades back we had analog mobile phones. It's something like a brick. Okay. But you can use that one killing a person other than taking a call. Okay, it's so big. But today's mobile phones, comparing to today mobile phones, they are very cute and they are very small. And sometimes that you when you compare your smartphone, it may be a little bit big than small. But anyway, that most of those things are small in size and it gives more features. And what about the power consumption? Most of the time it may be low power, low power consumption. And what about the cost? And when you compare the prices of the computers, I'm taking one example that now in the market that we have i7, i5, and like the type of kind of computers there. But couple of years back, we had different microprocessors and different generation microprocessors. And before that one also, we had a core to duo, core to code kind of microprocessors. But computer prices are same most of the time. It may be around maybe 50,000 and 100,000 between those things, and you can buy a computer. And today prices are also without, if you don't think about these taxes and other things, that most of the computer prices are they're falling into that margin. Okay, then actually that when you compare to the improvement of the technology and the features availability and maybe the facilities available, and it's a cost effective one. Why? We have today's computer the same price that we computer, when you consider computers that maybe the 1 decade back, those years also we had the similar prices for the computers. Then, but the technology advancement is there, but more features are there, more powerful calculations we can do, and lot more computing power is there. But price is maybe almost same. Then, because of that, we can say those products are low cost product. And like that, lot more features you can mention here. Then you can see that all these things are okay. Then because of these things that people very much like to buy these products. And sometimes that it may be most of the people are like to say that oh, my phone is digital and my monitor is digital like that. And not only that, other than this a technical word, today's world is a more maybe that most of the time it's a marketing word. If it is possible to wrap something with a digital wrapping paper, you can sell anything most of the time. Luckily, we don't have digital hoppers and digital photo today. Otherwise, that we'll buy it. Okay, then because of these reasons, or maybe some other reasons that considering all these things, and we like to buy those things. I'll ask one question from you. Maybe that sometimes that you may be a movie lover. You are watching movies much more. And when you watch movies and something like that, to get that the better feeling about that, you need a good sound system. Okay, assume that you are going to buy a new sound system. Okay, one assumption is there, you have enough money. Okay, with that you are going to an electronic store, and when you stepping into that one, you can see a lot more sound systems are available. And we can say the one side you can go there, the analog sound systems are there, and same features, high quality, and all these things are there. And the other side of the racks, you can see digital sound systems are there. Okay, let's assume that all these sound systems, whether it's analog or digital, both of them are providing same quality, and you have enough money. Which one you are going to buy? Which one? Yes, I got one answer, digital. Two, and maybe most of you are having the same answer like your friends. And okay, why? Because of these reasons. And what do you think about that? You can see that all the time when you go to the market, most of the things are coming in digital flavors and digital versions. And your washing machine controller, when you check your washing machine, and you have washing machine controller there, it's digital. And when you look at your air conditioner, the control is digital. And some other analog parts are there, some other electrical parts are there. But anyhow, that digital circuit is there. Controlling module, most of the time is digital. And your remote control, and your TV, your radio. That previously that we had a with the radios, we had certain knobs that we have rotate those things to tune the channel. But now you can press the buttons and you can select the channel number and for the volume also. You can press the buttons and you can increase and decrease volume. All these are digital. You can see that there is a trend in the world. All the things, if it is possible, they are converting into digital. Then we are throwing it away, that previous things, previous models, old models, and all these things, we are throwing it away. And we are accommodating all the digital version. Why? We like it. Because of certain reasons, because of so many reasons, we like it. Okay. That is a trend in the world today. I'm asking one question from you. Because of this trend, what do you think? One day, can we eliminate all the other products using digital product? Okay. Some of you have raised your hand. I'm going to catch you that. Do you have any question? Anything? Any question? If you have any question, you can write it there on the chat, or maybe you can talk. It doesn't matter. Okay, coming back to the previous thing we are discussing, and I'm telling you that that trend is there. Because of that, my question is, what do you think about that? Can one day can we eliminate all the products, and can we remove all the things from the world, and can we have a digital world, converting everything into digital versions? But if you have analog thing, analog phone, and analog TV, whatever the thing, that we can throw it away and we can use the digital version. Like that, the trend is there. One day, can we convert all these things into digital? Anyway, without taking much more time of you, the, and whatever the answer may be there, but still I didn't receive any answer. But the answer is no. Why? Because we are analog. The whole world is analog. Okay. When you look at the outside, you can see birds are flying, and wind is blowing, and trees are growing. Those events are not digital. Okay. But anyhow, because of these benefits, because of these features, we love to use digital products. But understanding that we can't convert everything into digital. What do you think about your parents' love? Is it digital? No, it's analog. Okay. Then so many things are there in the world. Because of those things, the world is growing. Okay. But anyhow, understanding these benefits and all the features there, we can go to the digital world and use it and take the benefits, and feel it and come back. Don't think that everything is digital. Okay. With that comment that we can move into the next thing. Okay, you can see that I have written there a couple of features. Because of these benefits, because of these features, we love these digital products. The next question is, what is the secret behind? What is the secret behind this? How these digital products are giving those benefits? Oh, what do you think? That the simple answer is logic states. All the digital systems, all the entire digital electronics and all the digital products are working on logic states. Logic states. Now we can talk about logic states. Now we are coming into the lecture, and from this moment onwards, we are talking about theoretical parts. Okay. What are the logic states? And we have two logic states. Maybe you can say on and off, or maybe you can say high low, maybe you can say black and white. Sometimes it may be 1 and 0. But anyhow, that we need two extremes to represent this one. One is on, the other one is off. One is high, the other one is low. But whatever the name you can use, it doesn't matter. But we need two different states, two different things, and two different ends to represent these logic states. It means that we have two logic states, but this is not the origin of these things. And maybe uh, when you consider this origin of digital electronics, it goes going around Second World War Two. Yeah, World War Two. The U.S. Navy, I remember, uh, and they have developed a certain system, but you know that in the war that most of the other parties are trying to catch the communication between the different parties. Okay, because of that they have to have a secret code to transmit their messages and everything, and they have developed certain kind of system having 10 logic states. Why 10 is there? To match the decimal number system. You know that with decimal number system, 0, 1, 2, 3, 4, 5, like that, up to 9, we have 10 levels, 10 numbers. To represent those 10 numbers, and they have developed 10 state logic. But fortunately, today we have only 2 state logic. Okay. Because of that, we need only 2 values, 2 different things to represent this one. Otherwise, we need 10 things. But when you understand, when you sometimes that if you have some kind of experience regarding those things, so maintaining a 2 voltage levels steadily in a certain period of time is not an easy thing. But maintaining 10 levels is a huge one. Because of that, today we are having only 2 state logic. 1 0 like that. And okay, now from this point onwards, what we are going to do, we are trying to understand to implement these two logic states in a place, in a thing. At the end, our aim is to become a digital designer, to become a digital circuit designer. Okay, to do that, we have to collect a couple of tools. We have to understand some of the theorems, to understand some of the concept. Then, from this moment onward, we are going to collect those things. First important thing is to understand about this logic state. You can see two logic states are there. Next thing, to match this logic states, okay, we need a kind of number system matching with our two state logic. Okay, what is number systems? And we have decimal number system, and decimal number system. Then here base is 10, base 10, and decimal digits are there. Digits 0 to 9, we have 10 digits. Like that, we have certain things. And some other number systems also there, octal number system. Then this base is 8, and numbers are 0 to 7. And binary number system. Base is 2. And what are the digits? 0 and 1. Okay. But I'm not going to discuss about this decimal number system and octal number system and other thing. But you can see that binary number system. But here with this decimal number system, we have 0 to 9, 10 digits there. Okay. Then 10 levels are there, 10 states are there. Then it's not matching with our two state logic. When you compare octal number systems, base is 8 and digits are 0 to 7. 8 levels are there, 8 digits are there. It's not matching with our two state logic. But when you compare binary number system, base is 2, binary digits are 0 and 1. Okay. This is octal digits. This is decimal digit, 0 and 1. Then you can see that these two levels are matching with this binary digit 0 and 1. Then hereafter, to represent these logic states, we can use this binary number system, and we can use this binary digits 0 and 1 to represent this two state. Okay. With that understanding, you can say digital circuits and digital electronics or whatever the thing is working on 0 and 1. But still you have to remember zeros, ones, and all these things are numbers. But digital systems, digital maybe the products are circuits. They are real things. They are electronic circuits. The electronic circuits, the electronic components cannot understand 0 and 1. But instead of this 0 and 1, the voltages are working. But we can't say the 5 volts, 0 volts, or 3.3 volts, 0 volts, 12 volts, 0 volts, like that all the time. We cannot say these voltage values. Instead of those values, we are saying high, low, 0 and 1. Those are representational values of the actual thing. The circuits are working on voltages, but those voltages are having two levels. the one in the other end. It may be 0 to 5, it may be 0 to 12, it may be 0 3.3, like that two levels are there. But all the time we cannot say the voltage values. Because of that, we instead of those voltage values mentioning that, we say circuits are working on zeros and ones. But we have to remember that actual circuits are not working on zeros and ones. They don't understand that zero and one. They don't know about those things. But anyway, that with that you have to understand that we are having these representational values. Then we can say 0 and 1. But hereafter we don't say this binary digits. Instead of that one, we can say bits. Then bits are 0 and 1. Okay. Now we have this number system, and here that we are not going to discuss those things at the moment today, but we have to have some kind of understanding about how to convert this binary number into octal and octal into decimal, like that. I think in your classes also, in your before your O levels and other classes, that you have done this conversion also. But I am not going to check those conversions, but I'll show some examples later on. But that is important that we should know about how to convert those things. But from this moment onwards, we are dealing with only binary numbers and binary digits. Then hereafter we don't say binary digits; those are bits. Bit may be a 0, bit may be a 1. Okay. Then it's a logic state, number systems. Then what else do we need? And still we didn't have any idea about that what type of mathematical methods, what type of mathematical operations we can do with these logic states. Do we need these maths? Do we need some kind of the mathematical input, or some kind of that maybe the uh, mathematical operations to be done with these circuits to implement certain things? It's most of the time to implement certain functions, to implement to certain kind of problems as a circuit, we need some kind of mathematical operations, maybe some kind of mathematical laws, logical laws, some kind of operations are essential. We need those things. Because of that, we have to take some kind of operations from our day-to-day world. But what are the normal mathematical operations we are using in our day-to-day activities? The addition, you have to add numbers, subtraction, division, multiplication, those type of mathematical operations we are using in our day-to-day activities. But here also we have to use some of these similar things. But can we use those things as it is? Can we use? What do you think? Okay, sorry for the interruption. But anyhow, that number system, and we are taking some kind of the algebraic concepts there, but you know that Boolean algebra, the entire Boolean algebra is based on two-state logic. It's not two-state logic, two states. It's true and false, like that. Okay. Here also we can write true and false. True false like that. The entire Boolean algebra is based on true false logic. Then it's 100% matching with our two logic states. But you can relax that we are not going to learn Boolean algebra there. Okay, here we are not going to learn Boolean algebra. It might take nearly 2 years. Much more time we needed to understand this Boolean concept in a greater level. But we are taking some loans from there. We are taking some kind of concept from Boolean algebra. Okay, then we are taking some kind of Boolean concepts. Okay, the first one is Boolean variables. Why do we need Boolean variables? Just anytime when you do something, when you make a system and when you make a function or whatever the thing, the variables are coming into the picture. But sometimes that because of certain reasons that maybe some of your previous experiences that you might not like this word variables and some mathematical operations and like that. But variables are not like that. They are really, really very good. They're beautiful things. Okay, but here variables is very, very easy thing. This one here. Why? These Boolean variables are having only two values. They're having only two values. That is true, false. Then very easy. Okay, when you see the range of these variables, only two things are there. One end is true, the other end is false. In between, nothing. Other than true and false, nothing else is there. Then this Boolean variables are very easy. Okay. Then if you say A is a Boolean variable, A is a Boolean variable, then sometimes A may be false. Okay. Then similarly we can take B. Then assume that B is a Boolean variable. Sometimes B may be true. Then this Boolean variable A maybe one time it's false and one time but anyhow that A is a Boolean variable, he can have a false or true value. B is a Boolean variable, one time it may be true, another time it may be. These are the values A and B can take. Okay, A false and another time A may be true. Those are the values it can take. Here it's false. Like that. Then this is very easy. And now we can take those things and now we can say that A false, A true, and we can say A may be 0 or A may be 1. The combining these true false values with our binary number system representative values 0 and 1. Okay. And hereafter we don't say true false. A is true, A is false. We don't say like that. We can say A is 0 and 1. then A can take two values only. One time it may be 0, another time A can be 1. Same for B also. Okay, then B may be 1 and B may be 0. So, 0. Okay, then when A is 0, we can say that is A bar. Okay, this is A bar. When A is 1, we can say that is A. Okay, hereafter, when the value of A is 0, we can say that is A bar. The value of A is 1, we can say that is A. Then we don't use true false, we don't use either 0 and 1 also. We can say A bar. When you look at that one, when you see that that is A, then you know that value of A is 1. When you see A bar, value of like that. Okay. Then what else we are going to take from this Boolean algebra? The next concept we are taking from Boolean operators. But when I write Boolean operators, you might not know this, but when I write those words there, definitely you know Boolean operators we are going to take not operator, not O, and no, none, and exclusive O. Those are the 6 basic operators we are going to take from Boolean algebra. And for these operators, we can say we can apply these operators for on our variables. We can take A and we can apply this not operation on A. And if you take A and B two variables, then you can apply this O operation on this two variables like that. Those are operators. We can apply those operations on the variables. Okay. But you can still understand that the digital systems they are real circuits. But to implement this not fun, not operation, O operation, AND operation, or whatever the things, and we need some kind of circuit blocks, circuit modules. Okay. And here, okay, these are the Boolean operators. Then, but these are actually all these things are paperwork, but we need some kind of circuit. Then this is some kind of circuit and it's providing this not operation. Then we have one input there and we have one output also. Then because of this not operator is doing always inversion of the input. When you input 0, it gives 1. When you input A, it gives A bar. When you input B bar, it gives B. Always it inverts the function. It inverts the variable value. Then when you give 0 here, output is 1. When you give B bar here, output is B. When you give A here, the output is A bar. When you give 1 here, output will be 0. That's what not does. Okay, but that is the definition of not. But we need a circuit. We need a circuit to do this. Then we have to find a circuit to do this one. We need circuit to do this one. Okay, otherwise that how can we build systems, digital systems? Then those circuits are logical devices. Actually, logical devices are, but when I write the next word, you know that these are logic gates. That is the last tool we are going to collect before we design circuits. Okay. In Boolean operators and logical devices. What are the logic gates? You know, not gate. I think some of you already know about those things, and maybe the couple of you might not know about that. But I am doing all these things from the grassroots level. It doesn't matter. You can follow all these things, and you have my word. At the end, you will have very easy subject there. You might not waste your time to read those things. And if you understand those things from very beginning, and very easily you can answer the question of this module. Not gate, or gate, and no, NAND, and exclusive or gate. And those are the gates. Then to have a complete knot, and most of you have known all these things, but anyway, to have a complete one, I'll explain this one very quickly. But if you have any kind of problem, then you can raise your hand, and or maybe on the chat you can write anything. Uh, Recently you haven't written anything on the chat. Okay, I think you know about all these things maybe before that. Okay, anyway, we are going to discuss about these things one by one, taking one by one. Gate, circuit symbol, truth table, and notation. The circuit symbol of the NOT gate is this one. With this NOT gate, we have one input and one output. And truth table is something like this. This is a Boolean variable A. Because of that, A can have two values, 0 and 1. When you give 0 to this input, not gate, what not gate does is that it inverts this one, then it will give output as 1. When you give 1, output is 0. The notation is all the time, this is A bar. Then you can say here A bar. Okay. Likewise, if you have any kind of question that you can, at any time you can interrupt me. Likewise, we can write those things for other gates also. The O gate, the circuit symbol is this. Minimum O gate needs two inputs. Maximum there is no limit theoretically, but minimum we need two inputs. This output is F, but here to make a truth table, we need two inputs, A and B. These are the all possible combination for A and B. When A is 0, B may be 0. When A is 0, B may be 1. When A is 1, B is 0. And when A is 1, B is 1. And those are the all possible combinations. And this is truth table. O gate is if any input is 1, output will be 1. Okay. Notation is A plus B. This is A plus B, A bar. When you give this one, here you can receive AOB. Yeah, the question is raised that the Boolean operators and logical devices are the same. Actually, the Boolean operators are there. Boolean operators are and not known and like that. The logical devices are the real devices we have developed to implement those Boolean operators. Boolean operators are somewhat those the paperwork function that you can write on these things on a paper, and some kind of that those operations that you can apply to certain Boolean functions, Boolean variables also. But the logical devices are the real circuits we have developed to implement those Boolean operators. Then AND operation is there, but to implement this AND operation, we have developed AND gate. Then what AND gate does is it gives AND function to the circuit. Okay. Okay. Then we'll say AND gate. AND gate circuit symbol is something like this. It also has minimum 2 inputs. Maximum theoretically there is no limit. This is output, and the truth table is something like this. These are the all possible combinations. But the AND function is when both inputs are 1, both inputs are okay, both inputs are present, output will be 1. But any of these things are 0, output will be 0. Okay. Notation is A dot B O A B. With dot or without dot, you can write it. This is A dot B. That all the time, if you want that, you can write without dot. Here also. Next one, no gate. No gate is actually not 100% new thing. It's a kind of O plus not combination. But here also you have to have minimum 2 inputs, A, B, and this is the output. It's something similar to this. You have O and NOT gate separately. But this is the no gate. Truth table. You remember this one. This is O gate. Output is 0, 1, 1, 1. Then no is opposite of those things. Then this is 1, 0, 0, 0. Up to this point, that is operation. Then after that we have send operation through a NOT gate. Then everything will be inverted. The notation is AOB bar. This is you can see at this point we have a plus P AOB. After coming through this NOT gate, we are putting inversion on top of that. Next one, NAND gate. Again, it's something like this NO gate. We have AND gate. Minimum we need 2 inputs. Maximum there is no limit like AND gate. But the notation is, truth table is this one. Okay, you remember the AND gate truth table is a 0, 0, 0, 1, and this is opposite of that one. It's 1, 1, 1, 0. The notation is A dot B bar, or you can say AB bar. This is A dot B bar. Or you can say AB bar. Like previous one, here also we can draw like a combination. This is a AND O combination. You can say here we can say AB. This is AB bar. And last one, exclusive O gate. It's a different one. something like O gate, but you can note the difference between that symbol and this one. So also the truth table, here when the inputs are both are 0 0 same, output is 0. When both inputs are same, output is 0. When both inputs are different, 0 and 1, 1 0 like that, then output will be 1. The notation is A exclusive OB. This is the notation. What do you think? Those are the logic gates we are going to use to make circuits, and then we have to divide our problems into small pieces. Then those pieces will be developed using these gates, and the problems of these small pieces will be addressed by using these gates. Then finally you will have a large circuit. That circuit is the solution for your problem. Okay, but maybe in couple of minutes time you can start designing your own digital circuits for moderate problems, small problems. Uh, but before we go there, do you have any questions? What is the real meaning of these things? This O gate and AND gate? O does what? Actually, if any input is there, O gives one output. Okay, but AND is not like that. To take an output from AND gate, both inputs should be there. Both inputs should be true. Both inputs should be 1 1. Then only AND gate provides this output. Okay, you can use it appropriately. You can use those functions appropriately to address your problems, to make a solution to your problems. Okay. For example, shall we, without remembering those things, those truth tables by heart, I'll show you small problem here. Okay. Now assume that you are a designer. Okay. One client is coming to you, and one customer is coming to you, and he's telling his problem. What is his problem? Now he has a room like this. Okay. Now he has two entrances. First entrance is A, the other entrance is B. Okay. He's telling to you that with my room I have two doors. According to my requirement, if one of these doors are open, I want to turn on alarm. That is his requirement. What's the requirement? He's telling to you to make a circuit to address my problem. My problem is I have room with two entrances, two doors. If one of these doors are open, at least one door is open, I want to sound an alarm. Okay, that is his problem. Okay, then assume that maybe we have fixed a door sensor here. That door sensor is providing a signal indicating that, identifying that whether door is open or not. Okay. Here also we have placed a door sensor. That door sensor is providing that one. It can identify whether door is open or closed. We say these sensors are digital sensors. Then 1 means door is open, 0 means door is closed. Okay. Now you are taking those two signals there, and you have to check one of these doors are open. Then what is the logic gate here we can use to implement those things? Which gate is giving that function? Which gate is fulfilling this function? What is our requirement? If one of these doors are open, we have to sound an alarm. Okay. Yes. Most of you have written O gate. Yes, that is answer is O gate. Okay. Why? The O gate is something like this. If one of these gates, if one of these lines are one of these inputs are one, output gives one. Okay. Then our solution is O gate, and you can take this one to an alarm. Then if one of these doors are open, then definitely this logic gate will check it, and if one signal is there, it will turn on this alarm. Okay. So now your problem, you have solved his problem. Okay, assume that after maybe couple of months time, he's coming again to you. No, no, no. This is a real headache that if one of these doors are open, the alarm is sounding. I don't want that. I want to change that logic, my security condition. Now this time I think that my security condition should be if both doors are open, then alarm should be sound. So he's telling like that. Then what is the solution? And yes. Now then you can have a different solution here, and you can take this AND gate. You can remove this O gate one. The signals are coming from A and B from these two doors. You can put it here, then the problem will be solved. Okay, likewise, you can see it's a very easy thing. If you understand the problem very correctly, then you can find solution. But to find solutions for any kind of problem, it may be simple to moderate to very high-end solution. It doesn't matter. All the solution we are providing using these 6 basic logic gates, nothing else. If you know about these 6 basic logic gates, that is much more enough. Then you can find any solution using those 6 gates. Okay. Now we are ready to start designing. Are you ready? What do you think? Are you confident enough to start designing? Now, do you believe that you are a digital circuit designer now? Yes, you are. Okay. But before we do that exercise, before we do that one, I'll give a small exercise to you. Can you try to write output values for these things? For example, I'm taking first one. I'm drawing a small circuit. This is AND gate. This input is A. This input is B, then you know the output is A and B. But if we send this one through a NOT gate, then what will happen? From this end, we receive AB bar. Okay. Now this AB bar signal is there. Now we can take C like this. Now after that, you can take C here. Then we are going to put another O gate. Now one of the signal coming to O gate is, this one is AB bar. This one is C. What is the function of O gate? O gate is taking operation from this input and this input. One input is AB bar. The other input is C. Now it's taking operation in between these two. Then final output is this. Look at this diagram. See that anything is there. If you cannot understand, now please tell me. Any of these things are there which you cannot understand. Now you can tell me, because we are going to do some of these type of exercises now. Are you okay with those things? Yes. Can you write? Yes. Okay. Shall we try? But if it doesn't matter, the others are telling yes. But if you have any kind of problem at any time, you can raise your hand. Any time you can turn on your mic and you can ask any question. Okay. Then second diagram. Can you try this one? You can take a piece of paper and try your own.
Sir, can you please check the chat? Hello, sir.
Yeah.
Sir,
Hello.
can you please check the chat?
Okay. 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 I'll do like that. Hello. Yeah. You can check your one. Then this diagram here, this is A bar. And from this gate that this is, we are receiving A bar B. Because this gate is providing n function in between A, it's two inputs. One input is A bar, the other one is A bar B. And here we have C. And then this AND gate gives n function between this term and this term. One term is A bar B, the other one is C. But if you want, you can write this one like this also, without having a dot. Here, this is A exclusive of B from this gate, and from this gate, this is C bar, and this gate output is C bar D, and this one taking O function in between this C bar D, but is a no gate. Because of that, the entire thing will be inverted. Okay. Are you okay with that? Okay, now you know that when you have a diagram to write output Boolean functions, you know it. Okay, this is a conversion of a circuit diagram into a Boolean function. At the end, you can write Boolean function, Boolean equation of the circuit. Okay, can you try the other way? Okay, when you have an equations, can you try to draw circuits for that one? For example, assume that you have an equation like this, A B bar plus C bar D. Can you draw circuits for those things? G. Okay, shall we try these things? Are you okay with this diagram? Here you can see that A, B, C, D, we have 4 variables. C, D, then we have to make A, B bar. Then first, straight away we can take NAND gate. Then from this point we have A, B bar. Then we have to take C bar. Then using NOR gate we can take it. And here we have C bar D. Then after that we have take O operation in between those two. This one we can bring there. And this is F. A B bar plus C bar D. This one we have A B C. A B C there. Then we have to make B bar first. After that, to make this one, we can take 3 input OR gate. Then first input is A, the second input is B bar, third input is C. Then from this gate, we can take A, O, B bar, O, C. Now we have to make this term also. Then straight away you can take NOR gate and one input we can take from A, the other input we can take from C. Then this is A plus C bar. Then after that we can combine these two using AND gate. And this is G A plus B bar plus C A plus C bar. This one again we have A, B, C also. To make first one we can take exclusive OR gate. This is A exclusive OB. To make this one you can take exclusive NOR gate, but we didn't draw this exclusive NOR, but whatever the thing you can do, you can combine exclusive OR gate and NOT gate, then exclusive NOR is there. Then here from this point you can take A, this is C, then this is A exclusive NOR. And to combine this one we need another AND gate. This is H. This one we need A, B, C, and D also. First we can make this term. This is 3 input no gate. It's A, B, C. This is A plus B plus C. No. This one we can take NAND gate. And we can take A. This is B. And this is A B bar. And AC bar. Here we have A, and we need C bar. And this is A C bar. Then we need D bar also. Okay. Now we have these 4 inputs. Then we can take 4 input 4 gate there, and we can combine this one, this one, this one, and this one. Then finally you have J. That's it. Any question? Anything regarding one of these things? Is it a must to write the equation for the middle outputs in the middle, or else in the final output is enough? No, it doesn't matter. But at the moment that I am writing all these things, but one is the question is asking that is it a must to write the equation for the middle outputs in the middle, or else is the final output is enough? No, no. I am writing all these things because of the that at the moment you have to understand everything in a simple manner. But when you write final thing, when you answer the question and when you do your whatever the own thing, this middle point equations are not enough, not necessary. Only the final thing is the necessary one. But here I am writing all these things that you can understand that how these things are coming. Otherwise, that maybe in different day, when you look at this one, then you might have a problem that how this is coming like that. That's why I have written all the intermediate stage equations. But otherwise, it is not necessary. Okay. Now, what we have done here, now you know to write output Boolean equations when the circuit is available. And you know the reverse also. To draw the circuit when the okay, here what you know, then you have equation, then you can convert equation into circuit. Here what do you know, you have circuit, or the other way. When you know the equation, you can draw the circuit. But here, when you know the circuit, you can draw the equation. You can write the equation. Both ways now you should be able to draw. Okay. Now this is the all what you get today. But we have collected tools from the beginning, from logic states. We have discussed about the number system matching with our two-state logic. Then after that, from Boolean algebra, we are taking the sum of the concept, Boolean variables and Boolean logical operations. And for these logical operations, that we have logical operators, the logic gates to implement all the Boolean functions there. Then we know how to use those things, and uh, then now we are ready to design circuit. But before that, we should have some kind of idea that when you have an equation, how to draw a circuit, and when you have a circuit, that how to write output equation like that. You should know all these things, and you should have some kind of idea about those things. Okay, now you can refer this one, and if you are okay with this one, it doesn't matter. But otherwise, that if you are new to these things, that you can refer it again and again before we come to next class. But at the very beginning of the next class, you can ask all these questions, but if you have any kind of problems there. Anything else? Okay, the reference material actually that you can refer this one, digital systems design, Harry Wilkinson. And not only this, any kind of basic digital circuit design in books are okay. Okay. But if you have enough time, that it doesn't matter that you can refer those materials, but otherwise that you can come to the class regularly. I think that is enough. But for the broadening of your knowledge, that you can refer any material, it doesn't matter. It should be done. But otherwise that you can come to the class. We are doing everything from the grassroots level, from top to bottom to top. But if you're okay with that one, but if it is not possible to attend, that you can refer the videos and everything, but you can ask questions at the class also. But you have my word. At the end, definitely you are okay, and you can answer your question paper very well if you are going like this. Okay, but anyway, that I need your support. As I mentioned at the very beginning, this is your time. Full cooperation from your side is essential. It is necessary because you are doing these things, and because of now you know what to do to to climb the ladder in your future. Because of that, you have to have some kind of that responsibility to cover up all these things. And I think you have, all of you have that understanding. Then I am here to help you, I am here to guide you, and it doesn't matter whatever the time period that we are having. Outside of that time period is also, I'm ready to help you. But your input is essential, your input is necessary, and we can go like this until you see the happy end. Okay. If you don't have any question, we can wind up today, and let's meet next week. Okay. Thank you very much. Have a nice weekend.